Thank you for being here. This morning, we're going to kick off today with Pavel, his lecture series.
Thank you. All right, so there is not enough time. So I introduced some sort of finite dimensional linear algebra model for a field theory or H theory associated to an algebraic piece of data, unimodular differential graded Lie algebra. So this kind of field theory package or PV package associated to this algebraic data was the following. So it was the space of field, which we put something like tangent bundle of V, roughly speaking. So it's V with certain integration plus the dual with certain integration. So this space is my space of fields, a space of PV fields, and it comes with a symplectic structure of degree -1, the PV symplectic structure, and with certain action, which is a cubic polynomial on that vector space. And well, it turns out that this polynomial satisfies the quantum master equation. And this quantum master equation has sort of, on the left, there are four terms, which are, well, if I would have put some arbitrary operator here and some arbitrary bilinear map here, then these four terms would not vanish, but their vanishing corresponds to certain identities satisfied by the operation here and by the bilinear operator here, and the identities are the kind of structure identities in the algebraic input. So the fact that d squared is to 0, Leibniz identity, Jacobi identity, and the universality property. Now I want to play a game of kind of contracting that field theory to a smaller place, to a place associated to some subcomplex of V. So so my name for this package is abstract BM theory. Well, because somehow we abstract from the RAM algebra. So instead of here, I would have plugged in the RAM algebra. I would have recovered the usual BM theory. So now, collapsing this data to a smaller place. So the name of this game is effective action. So that's the physical name of playing the game, or effective VD actions. So or this abstract VM theory. So okay. So now I want to say something that maybe familiar to many people here. So okay, so let's fix a deformation retract of the complex of my complex V comma D. So let me forget for the moment the bracket. Just look at this algebra. Forget about the bracket and think of it as a complex. So then I want a subcomplex. So I want kind of a smaller complex with an inclusion I of the small complex into the large complex. I want a projection P, so they should both be chain maps. So and they should satisfy the P coupled with I its identity in W. So and I also want a chain homotopy K here, which is the chain homotopy between identity on V and the opposite composition, P followed by I. So dk minus plus kd is identity minus I composed with P. So I and P are chain maps. K is not a chain map; it's a chain homotopy. So it's left between -1. Let's find this equation. And I want also some kind of side conditions that K followed by P is 0, K composed with I is 0, and K squared is 0. So this such a package of data, so I, P, and K, so I will kind of pictorially draw it as as some kind of squiggly arrow from the big complex to the small complex. We will write these three maps here, IPK. So there are many names for this data. So the standard name in the literature is a strong deformation retraction data, so SDR data. So that's kind of the name in the literature. For some reason, I didn't know that name, and I got used to calling it IPK triple, or also induction data is another name for it. So this is the data that appears in cohomological perturbation theory. Okay, so let's say that I have fixed such data. Now, then what does it give me? So it gives me some kind. Okay, first of all, it gives me a splitting between. If I just use the inclusion and projection, then I have a splitting of V into the image of W plus the complement, and the complement is the kernel of P. So kernel of P. So let me also call it P double prime. So why double prime? Well, because I'm used to some notations where W is also called V prime. So kind of splitting P into the image of V prime and V double prime. So then what we have here is a splitting of V into the image of the small complex plus a complement, and the complement is acyclic. So that follows from the existence of K. So it's a splitting into subcomplexes. I think of this as a small subcomplex. This is a huge subcomplex, and this one is acyclic. So vanishing cohomology. Now, using the data of K, I can further split this acyclic part into the image of D and the image of K. So, so kind of refining this decomposition, I have a decomposition like that. So P double prime D, the exact part, and P double prime K. And this is some sort of abstract Hodge decomposition. And well, in some special cases, it becomes the usual Hodge decomposition. So, namely, if I take V to be the Durham complex of a Riemannian manifold, so let me take a Riemannian here, so that's an example. So then I can take W to be the cohomology of M, included as harmonic forms. So then I is inclusion as harmonic forms. Including homology classes as harmonic forms. Then the projection will be, so this decomposition will be literally the usual decomposition into harmonic of differential forms into harmonic forms plus exact forms plus co-exact forms. So the projection is, well, it takes a differential form and, well, orthogonally projects it onto harmonic forms. And let me write what is K in this example. What is the chain homotopy? So it is. So I should take the Laplace operator on differential forms. I should add to the projection to the harmonic forms and invert it. So I'm taking the positive Laplace and I should compose it with D star, the co-differential. So that's the chain homotopy in this example. The one corresponding to the usual Hodge decomposition. Okay, so then we have usual Hodge decomposition. Okay, now let's say that we have well, back to our sort of abstract setting. So we have some unimodular differential gradient Lie algebra, and we have fixed information retract and such an IPK triple.
Sorry,
Yeah, please.
Was P harmonic just a projection of the harmonic forms?
Yes, orthogonal projection to harmonic form. So that's P. Okay. Now, yes. So then I have the composition of the space of fields that I wrote here into well, similar kind of doubling, but of W. So f of W, so the f of V plus f of W plus f of V W prime. So, well, how so? Well, essentially, just using this decomposition for V, and then I have also a dual decomposition for V stars. Putting them together, I have a decomposition of this space of fields for V into the kind of slow part and fast part. So I'm thinking of this first summoned as slow fields or infrared fields. So in physics terminology, although low energy fields, slow or low energy, or infrared. And well, this sort of second summoned as fluctuations of fast fields or ultraviolet fields. Ultraviolet fields. So, okay. Now, the idea is that we want to start with our action on the big space and induce the action on the small space here, on this first summoned. So we want to define the effective UV action as W on FW, so on the first summon here, using the following formula. So we want to consider the exponential I over H bar of our action on the big space. So and then it depends on fields A and B, but now A and B are decomposed into a slow part and fast part according to this decomposition. So I want to plug here A in the slow part plus the fast field, and B slow plus B fast. And I want to integrate out the fast fields. So this SV is that action. So corresponding to the abstract BF theory on abstract BF theory associated to the DGB algebra B. So, but so I want to be sort of more precise about how I integrate here. So actually, I want to integrate over a Lagrangian or linear Lagrangian subspace inside the second summoned. So I want a particular Lagrangian here, Lagrangian subspace. So somehow among all possible pairs AW prime, BW prime, I'm sort of cutting out a half of those possible pairs. And how I'm cutting out the half, that's actually given by the choice of K, of the chain homotopy. So there's a Lagrangian here in the second vector. It's given by the image of K plus the image of the K dual. So image of K for the A fields and image of K dual for the B fields. So
sorry, so how do these subspaces interact with the symplectic form?
Yes, so this is splitting into symplectic subspaces. So the symplectic form is a direct sum of a symplectic form from here and symplectic form here, right? And then here inside this second symplectic space, I have a Lagrangian subspace. So that's how they interact.
So in this Hodge decomposition, this D exact and K exact
Here there were no symplectic structures
Right.
because it was not yet doubled. So symplectic structures arise when you double things, right?
That's right, yeah, so you double this, so you double this T exact and K exact thing, right?
You want here?
Yes,
Yes. So I'm doubling. So I'm sort of adding to this another line, which is so okay. So I have that the dual is the dual in the dual transpose map of projection applied to W dual plus here it will be like, okay, if I'm modeling that part, it would be like the kernel of I dual. So when I dualize sort of the direction of the arrows reverse, I need to swap I and P. And sort of the second part again splits into two pieces, and I take sort of in both cases the second piece into my Lagrangian, and I'm saying that the first piece should be 0.
okay.
My Lagrangian.
Can you help me understand conceptually why this is a sort of UV-IRD composition, or is it?
Yeah. What happens here is some kind of model for Wilson's generalization. So we're integrating out fast fields and leaving out the action on slow fields. So in the original Wilson's picture, you had I don't know, you're thinking about something like scalar field theory, and you think of fields. You sort of think of fields in terms of the transform. But then you have sort of in the momentum space. So you are integrating out kind of fields with large enough momenta and consider the resulting action depending on fields of small momenta. So this is kind of a spherical layer. You're integrating out a spherical layer in the momentum space. So the part that I'm integrating out is this part, and the part that I'm leaving in the game is this part. So that's kind of going back to 70s and Wilson's, or maybe 60s, and Wilson's RG flow picture. In my example, it would not be literally that. It would not be literally doing the Fourier decomposition and leaving some kind of small momenta in the game. Rather, in the game that I'm playing, this will be a cochains of a triangulation, and this will be some sort of complement of cochains, but sort of the ideology is the same. Mm-hmm. Okay. All right. So yeah, the reason why I have to integrate over a Lagrangian inside this fast fields rather than all fast fields is somehow because we are in the BV formalism where the field content is doubled. So somehow this integral would be way too degenerate if I were to try to integrate over all fields. So somehow to make it perturbatively well defined, I need to cut the space of fields in half, which is achieved by choosing this Lagrangian. So then, okay, then this will, so the logarithm of that will be called the effective action. So it's the action of W, which is a function of the slow fields and also a function of H bar. So it's defined like that. So, all right. Now, just to draw a picture corresponding to this, what's going on here. So this is my picture for the space of fields, and I'm thinking of it in terms. Well, I'm thinking of this right-hand side as well as a trivial vector bundle where the base is FW, and the fiber is F V double prime. So then. What I'm doing is I'm doing a fiber integral, but in each fiber I'm choosing a Lagrangian L. So this sort of big fiber is moving along FW. So fixing a point in FW, which is a pair AW comma BW, I'm integrating over a Lagrangian in the fiber over that point. So the result will be some number. So, and this number would be, well, the exponential of the effective action for that kind of AW. Right? So what I'm doing is kind of this fiber integral, but where I'm picking a Lagrangian in the fiber.
So it doesn't depend on the other direction in the fiber?
I'm integrating out so the integrand. So it does depend on the whole fiber. It does depend on the other direction, but I am choosing some Lagrangian, and that's the choice of gauge fixing. So the choice of Lagrangian is a choice of gauge fixing. So then I might ask the question: what will happen if I change my Lagrangian? And I'll say something about it. So somehow the result will change by an equivalence or quasi-isomorphism in the appropriate sense. Yes, please.
Sorry, what's the last variable in the left-hand side of
H bar.
H bar?
Yeah, sorry. It depends explicitly on H bar. The result. Actually, I will write more explicitly what's in our setting this effective action piece. Okay, so now let me say something that we should expect from the result, and actually for finite dimensional BV integrals, that's a theorem, and that's kind of it's a consequence of something that's kind of informally is known as BV-Stokes theorem. Let me not try to phrase the general thing, but rather the implication for the case at hand. So first implication is that knowing that SV satisfies the quantum mass equation implies that SW satisfies the quantum mass equation. So and the quantum mass equation can be written as the fact that the BV Laplacian on FW applied to the exponential of SW vanishes. So that's the same as it's equivalent to writing the quantum mass equation in the way that I was writing it up to now. That's vanishes. So right. Okay. The reason why this happens. So well, the integrals can be converted into usual fiber integrals by something called odd Fourier transform. So then the usual Stokes theorem for fiber integrals, that if you have a fiber bundle and you have a differential form, you have a closed differential form on the total space of the bundle, you do the fiber-wise integral, you obtain a closed differential form on the base. So up to this odd Fourier transform, it becomes this state. So because the round differential on the total space and on the base up to the odd Fourier transform become the BV Laplacian on the big space, BV Laplacian on the small space. So it's ultimately a consequence of usual Stokes theorem. And another consequence of also usual Stokes theorem under this transformation odd Fourier transform is that well, exactly the question of what happens if I try to change this gauge fixing. So if I have a family of Lagrangian subspaces here, so depending on some parameter t, so a smooth family of Lagrangians, then, well, for each kind of member of the family, I can calculate the corresponding effective action. Let me call it SWT. So it depends on the Lagrangian in my family. So then it turns out that that they change in a sort of nice and controlled way. So the change, the speed of that change is can be written as follows. Minus IH bar delta RT. Well, it's delta is W. RT is certain function of degree -1 on FW, and so what's written here is so-called infinitesimal canonical transformation. And another way to write it is that the implication of that is that the exponential of SW changes by okay, if I take its derivative in t, then it's delta exact. And what's written here depends on this generator R. Right? So what we have is some kind of homological picture, so that the exponential of the action is delta closed, and if we start changing the gauge fixed in Lagrangian, it changes by delta exact term. And moreover, if we're diligent, we can write down the generator by which delta exact term changes. All right. Now, so that was some kind of general discussion of BV fiber BV integrals. Now, but what happens? Can we write something more explicit? Like what is this SW? So I wrote some kind of integral formula. Maybe we can compute it. And the answer is that, well, yes, we can compute it. So in terms of kind of perturbative technique as a sum of Feynman diagrams. So the answer Feynman diagram computation, or the answer of Feynman diagram answer, I guess. Computation of SW. So it gives me the following answer, that SW is the sum over binary rooted trees. Binary rooted trees. Let me call them gamma 0 and 0 for the fact that they can zero roots. So, okay, and then let me draw some kind of sample tree here. So I orient them towards the root. I put the inclusion of the field AW on each leaf. I put the leaf bracket in the algebra V in each vertex. I decorate each edge with negative chain homotopy. And I decorate the root with, so I'm kind of going from the leaves to the root. And so when I reach the root, I obtain, okay, some kind of object in V. Then I should project it to W and pair with the fields V. So the result, so the value of each Feynman diagram then is some polynomial on FV, on FW, sorry, on the space of slow fields, which is linear in B and of some degree in A, and which degree is the number of fields. So
sorry, let me just back up to make sure I understand. So the when you talk about a rooted tree, does that automatically mean that all the edges have a direction?
So I want to orient it towards the root, and there's a unique orientation like that. So
okay, and then the key was the homotopy.
Yes.
What does the binary part mean?
There are at each vertex there are two incoming and one outgoing edge. So binary means two incoming.
I see. So you don't.
I'm not allowing one.
See, you talk about like incoming and.
So there will be always one outgoing. That's kind of a property of a tree. Tree directed towards the root. But the number of incoming edges could be in principle different. And so the fact that it's binary corresponds to the fact that I have only a binary operation in V, that I don't have higher operations. If I were to have higher operations, then I would allow higher valency vertices in the tree.
And then you write I of A.
The AW, sorry, I of AW, yes.
So that's just AW lives on like the thing.
AW lives in W.
Yeah, so
I include it into the big complement.
So the same thing you should do with the BW or.
I could I could do that, and then there are equivalent ways to write it. I could do what you say, and then I would apply P dual to BW. and pair with the result. That's kind of equivalent to what
I see.
I wrote. This was a pairing in W, this would be a pairing in V.
Okay.
They're just equivalent ways to write it. All right. So maybe just, simplest example. So if,
Sorry, I don't, the very last thing is that like you have this outgoing edge, right?
Yeah.
And is it the edge or is it the vertex at the outgoing end that's labeled by this sort of pairing?
I think of this as half edges. So the external leaves as half edges. So this half edge, so it doesn't get decorated with the chain commutator. Only the internal edges are decorated with the chain commutator. So this one is decorated by this operation. Maybe for simplicity, let me just draw an example. So, and explicitly write what's the corresponding expression. So for instance, for this G, the corresponding expression would be, so I should put I of AW at each incoming edge. I of AW, and I should put minus K here. So let me just write down the corresponding expression. So I should do the bracket of I of AW with I of AW. I should apply negative K because then I'm going by this edge. Then I should take the bracket with another I of AW coming from here. And then I should project back to the small complex and pair it with BW. So that's what it is.
Okay, thank you.
So, let's see. Here the trees are actually trees up to isomorphisms. So they are kind of not without fixed planar structure. And then I should also put here one over the number of automorphisms of the tree. Precise. So that would be 1/2 for this tree, for example, two automorphisms. So, and then there's also another family of graphs that I should take into account. That's one loop graphs. So one loop graphs. Let me call them gamma 1 because they're one loop. Again, so graphs maybe like that. So what's a one loop graph for me is a single cycle with a bunch of trees plugged into that cycle. So with root kind of planted into the cycle. And again, let me explain how to associate an expression to such a graph. So I should cut this loop at some place and then sort of unwind what the result into a tree, which will have some kind of distinguished input. So the value of that tree, according to previous rules, would be some kind of operator that eats the input here and spits out the input at the end of the tree. And then I should take the trace of super trace over V.
Sorry.
Yeah, please.
Determine which one is the input, does it matter? You have the directions.
Yeah, but in fact, it doesn't matter. And also you can cut it in an arbitrary place and it will always be the same answer by cyclic property.
Oh, just like picking which direction.
Yes, the direction in the loop also doesn't matter. So yeah, you can prove that. I mean, you will write different expressions, but they would be equal. So, and let me maybe show you maybe the simplest example. So if I take, for instance, this one loop graph, so then I put I of AW on each leaf. So there's K, let me orient it somehow. So there's negative K on each internal edge. So then, and let me cut it here. So then what I have is I have some kind of incoming element of V. So I take its bracket because also each vertex is colored with bracket with I of AW. So take such a bracket, take negative K of that. So I'm here. I take the bracket again with I of AW. So then I'm here now. I apply negative K, and then I'm here. So I'm back to the starting point. So and now I take super trace over E. So that's the value the value of this graph. Yes, please.
Is there a reason why we put AW?
Come again?
Why do we put AW? Like, is there, why not leave them?
Yes, so that actually has to do with orientation. So I mean, these rules they're not arbitrary. This is a computation, kind of a stationary phase computation of that integral. So my leaves, so or half edges, they have orientation, and this orientation corresponds to either A field or B field.
So why is there no BW in this one loop?
Okay, so in this integral, so there's the cubic term, which is has two A's and one B. So this corresponds to me constructing graphs out of such such internal vertex, and then I'm also allowing leaves here, loose half edges corresponding to well, AW and BW. So if you think what connected graphs can I put together from such vertices, you will realize that those are the only possible ways. So you can have either zero loop connected graph with a tree, or you can have a one loop graph which has only incoming half edges. So that means that there's only the A field there. Why this is so? Well, it's a nice exercise which, for instance, you can prove it using just looking at the Euler characteristic of graphs.
So the B's sort of are in the loop, but then they don't appear in the end. Like you're
B fields, yeah, fluctuations of B fields. You can say that each half edge is a propagator between B double prime and A double prime.
Yeah.
Yes, each propagator. Yeah, you can think of it like that. Mm-hmm. All right. So yes, so this is kind of a formula. So it has lots of terms corresponding to different graphs, but each term is something very well defined. So
Sorry, give me that. But then,
that should be the number of automatisms. Yeah.
sorry, one more question. So why there is no two loops? That's because
Again, the same reason. So if you just trying to construct a two loop graphs, oriented two loop graphs where each vertex is oriented like that. It's connected two loop graphs. That's impossible. So yeah, this is somehow an interesting feature of BF theory that there are no parallel loop graphs. They kind of unlike, for instance, Chern-Simons theory. So in BF theory, these graphs are oriented, which sort of is a very important point. Having oriented graphs is related ultimately to having the space of fields, which is split into like canonically split into V and V star. So okay, so I think I explained the diagrammatics. So I forgot. So I'm speaking until 10:30. Yeah. Okay, so let's see. Yeah. So yes. So now by the Stokes theorem, which I sort of claimed here. So by the point one, the resulting effective action satisfies the quantum master equation. So, in fact, so okay, maybe let me just write again the kind of what's called the Feynman rules of how like the rules for associating expressions to those pictures. So an internal vertex is associated is decorated by the commutator. An internal edge is decorated by negative K. And leaves, well, depending on the orientation, are decorated by either the A fields or slow A fields or the slow B fields of the leaf, like the star of the B field. Okay, and the loop is decorated by the supertrace. So okay, so as W satisfies the quantum master equation, and it's on the one hand, it's just it just follows from the Stokes theorem for the integrals. On the other hand, there is a purely diagrammatic argument for proving it. So can prove it directly from diagrams without resorting to the PV integral. And the proof is, well, essentially you split SW into its free part, corresponding to just the quadratic term corresponding to D to the differential on W. So there will be the free part, which is, well, secretly, it's kind of a particularly degenerate tree that should be, that corresponds to the term, plus, so let me call it S0, plus everything else, the perturbation. Then you can calculate the Poisson bracket of S0 with I, and well, that would correspond to some combinatorics where there is kind of a D operator that sort of hits one of the leaves of a graph, and when you sum all these terms, that using the properties of the D operator, it will become a sum over graphs where with one marked leaf, and the marked leaf will be marked by the anti-commutator of K with D. So, and then well, then each stage internal edge will be, okay, identity minus projection to W. So the terms with identity will cancel out due to graph combinatorics. And the terms with projection, they correspond to well, the missing terms in the master equation. So roughly speaking, you will be calculating this Poisson bracket, and you will obtain that it's well, up to signs, it's the terms where you're cutting one leaf of the marked leaf in a graph, and these terms corresponds to either calculating the bracket of SW with SW, or calculating the PV Laplacian of SW, depending on whether your cut leaf is sort of, when you cut it, whether the graph splits into two subgraphs or not. So then it's either here or there. So I sort of mumbled through this argument, but it's what I'm trying to say is that there is an argument which does not rely on PV integrals, which is very useful, because although now we're kind of playing this game where B is finite dimensional and we can really rely on those integrals, we ultimately want to go to the case when B becomes the Dirac complex, and then sort of the PV integral becomes much more iffy. It's a path integral then, and Stokes theorem becomes sort of Stokes, wish, or PV Stokes wish, yes. So, and then the diagrammatic proofs, they sort of become the correct mathematical proofs. Okay. And so there's the diagrammatic proof of the master equation, and there's also diagrammatic proof of the fact that if I change the gauge fixing Lagrangian, then SW is changing by canonical transformation. That can also be proved from diagrammatics. All right. So now, yes. So this SW, so it's not. It doesn't satisfy the ansatz of abstract BF theory because, well, it has terms of high order in AW, but rather it satisfies some more general ansatz. So, which I will call BF infinity ansatz, which is kind of a generalization of this one. So, well, the space of fields for this effective theory is still W plus W star, but the action and the form is canonical, but the action is more general. It's slightly more general ansatz. So it's a sum of terms like that. So linear terms in B and some, and here it's very close to what Konstantin was writing yesterday. So there will be some familiar objects. So this is Ln is some multilinear n linear operation that takes n inputs in W and they put AW as the inputs. So and then there's kind of an H bar correction, 1 over n factorial Q and W of AW dot AW. Also n inputs here. So this Ln and Qn, they are multilinear operations. So Ln is takes n inputs in W and spits out an output in W. So and does it skew symmetrically? So it's a skew symmetric operation of degree 2 minus n. And Qn takes an input and spits out a number. So these first family of operations, so n from 1 upwards, so these are the L infinity operations.
Sorry, but is the exponent of Qn in the form
W, sorry, it's
W? Oh, okay.
W. So kind of operations on W.
Yeah.
Mhm. So so these LNs or LNW, they are skew symmetric L infinity operations on W, and Q and W are some kind of new operations. So let me call them quantum operations, or one loop operations if you like. And their degrees are negative n. So and these operations, they satisfy a bunch of relations. Maybe erase there. So the operations Ln satisfy the usual L infinity operations, which are kind of the Lie version of the A infinity operations that I was writing yesterday. So the first family of relations is that, well, let me draw it schematically. So if I take an operation L r plus 1, of arity r plus 1, and then I have some inputs, where the last input will be the output of the operation ls. And I have s inputs here. So if I sum over ways to split n into r plus s, so then I have n inputs here, then this sum should be 0. And so if I have an output, and I should also be skew symmetrizing over the inputs. And so if implicitly I'm also skew symmetrizing over the inputs. So that's the usual L infinity relation, or homotopy Jacobi identity L infinity relation. So the classical L infinity relation. But then there's also the quantum L infinity relation. So let's call this sequence 1, and sequence 2 will be the following. So I should take Ln plus 1. So it has n plus 1 inputs. And I want to take its kind of partial trace. So I want to fix first n inputs, consider it then an endomorphism of W, and take the trace, super trace of this endomorphism. So this loop means take the super trace. So then this super trace plus the sum over ways to split n as r plus s of, and then I write what's written here, but replace its second operation with a quantum operation. Q r plus 1 with a bunch of inputs, and the last input is the output of ls. So such a sum, again, skew symmetrizing over the inputs, it should be 0. So this is kind of these two sequences of relations. They are the kind of correct up to homotopy version of a unimodular differential graded Lie algebra. So I am calling such structures quantum L infinity algebras. Another name for them is unimodular L infinity algebras. So you can think of this sort of what's written here as a kind of up to homotopy condition of unimodularity. That's the last condition on that board. So yeah, so these relations here, they are not sort of ad hoc. it's actually the quantum master equation for this action. So if you write down the quantum master equation, look at various terms that have to vanish there because it's polynomial. So that would be exactly the relations that you get. And so the coefficients of kind of the monomials in S correspond to the operations, and the quantum master equation corresponds to the quadratic relations in this algebraic structure. So the logic then is the following. So what's going on? So we started with a unimodular differential graded Lie algebra V. So with its operations, there were two operations, theorem and bracket. We associated to it some kind of PV package, which I called abstract PF theory. So it's consisted of a space of fields, symplectic form, and the action. And this action, the action was containing the data of these operations. So then we did the compute the effective PV action. Or performed by the PV integral. So we obtained some kind of on a smaller space of fields with its symplectic structure. We obtained some kind of effective action. So we computed this effective action. Then we can look at it and read off the monomials in that action and interpret them as polylinear operations. So so what we obtain is a quantum L infinity algebra structure on W. So W was a deformation reject of V. So quantum L infinity algebra corresponding to let's see, two sequences of operations Ln and Qn satisfying appropriate conditions. So so then I can sort of look at the formula at these formulas and sort of reinterpret them as formulas for these induced operations as coming from the operations upstairs, and in particular formulas for the classical operations. They kind of it's a Lie version of formulas that were known in the literature as homotopy transfer formulas, and so I don't. So the history is a little bit convoluted of who wrote them first, but apparently, either Kadeshvili or Kantsevich-Soberman. And they sort of wrote them in words, not as a formula. But in any case, so the classical part here is the kind of Lie version of the known sum over trees formula for how we transfer an algebraic structure to a subcomplex. And this Q part is sort of some new formulas, or they were new when the paper was written. So okay, and now that was sort of the linear algebra or finite dimensional setting, and now I want to sort of go to differential forms. So okay. Now, now I want to sort of break the rules of the game and apply this transfer process to, going from the infinite dimensional algebra.
Could I ask a quick question? So if you would start instead of with a unimodular DGLA, you would start with a quantum L infinity algebra, and then you have the retract of that. Then do the same transfer formulas work?
Absolutely. So and then yes. So that's the situation when you would have sort of Feynman graphs. So yeah, you can repeat everything, and then you would sort of you start with quantum infinity algebra. You assign kind of a BF infinity package here. So and then you calculate the effective action, and it will be a very similar formulas, but you will have sort of higher valency for invertices here, and you would also have one new type of vertices, which will be sort of this quantum vertices, which have no outputs, which have several inputs and no outputs.
So the same way as the DG Lie algebra is a special case of a L infinity algebra, you're saying a unimodular DGLA is sort of a special case of a quantum L
Yes.
infinity algebra.
Absolutely.
Okay.
Yeah, exactly. And this sort of stabilization is indeed very important because we would like to be able to repeat this process and do it several times. That would be very much in the spirit of Wilson's sort of effective action, because that's supposed to be a repeatable process. So you should be able to go to smaller and smaller subcomplexes until you go to the smallest one, which is homology. So,
Question. So, fact infinity algebras in compared to zero are the same as
no. L infinity algebras, they're more general. So for sure,
we can sort of twist like this consideration zero.
well, I mean, you can find quasi-isomorphic DGLA, but there are certainly L infinity algebras.
I understand. The question is that how the structure is more rigid than just.
Yes. This is yes. So a quantum L infinity algebra is sort of, it's a condition and a structure on a usual L infinity algebra. So you want certain combinations. So not to every L infinity algebra you can add quantum operations to make it a quantum L infinity algebra. It's a condition. This extendability is a condition. So it's condition plus a structure, a choice of those Q operations.
Sorry. If we drop the unimodularity property, how can we verify quantum mass equation?
You cannot. It will not be true.
Yeah. So
It's just not true.
So can we still do the homological?
Modulo H bar, right?
Yeah.
If you want to have H bar in the game, you have to. Yeah. Okay, so now the next sort of direction where I want to go is I want to start from the round complex of the manifold, and I want to go to a chain of a triangulation. So T would be the triangulation of a manifold. So that would be my V, and that would be my double. Of course, I'm breaking the rules of the game here because V suddenly becomes infinite dimensional. So I need to sort of, close my eyes and, jump there and see what happens. But there's kind of an interesting part of the story here is what's the corresponding IPK triple. And there's kind of a nice choice here. It's quite non-trivial, but it leads to nice results. Somehow a choice of an IPK triple, which is compatible in a certain way with triangulation, somehow such that in the results, the simplices that are apart will not be talking to one another, so compatible with some version of locality. So, and this is the construction which, well, let me call it Whitney-DuPont construction. I will start explaining it and we'll continue in the afternoon. So, on a standard n-dimensional simplex, so that's kind of points in Rn plus 1 with such that all their coordinates are in the negative and the sum of coordinates is equal to 1. Standard n-dimensional simplex. So on such a simplex, Whitney introduced something that he called elementary forms. And they are assigned to various faces of that index. So if I have a face, a k-dimensional face corresponding to a increasing sequence I0, I1, ik of vertices of my simplex. So it's a k face. So then the corresponding differential form is the following. So it's a sum from zeros to k, -1 to the j, t I j, dt I0, wedge to the dot, I omit dt I j, dt I k. And let me maybe just finish with finish this talk by saying how it works for an interval, which is a one-dimensional simplex. So there are two pericentric coordinates, T0 and T1, which add up to 1. But let me express everything in terms of T. So then for an interval, the corresponding Whitney form chi0, corresponding to the left side of the interval, is T0, which is 1 minus T. So it's this 0 form. Chi1 corresponding to the right endpoint is T1, which is T. And I01 is so corresponding to the bulk interval is the bulk of the interval is the one form dt. So Whitney forms realize a very nice chain inclusion of cochains of the standard simplex with standard triangulation interfaces, a chain inclusion into differential forms of the simplex. And I will continue from this point. Thank you.
Questions for Pavel?
Can you do something similar for other quadratic quadrats?
For other words?
Quadratic quadrats.
Oh.
This looks like something of the other
Yes.
Indian
Yes.
between the blue and one.
Yes. That's a good question. So some part of the story I think you can do for other operas, but then so having L infinity here is kind of natural because you like commutative spacetimes. And maybe other operas will lead to very, very weird sort of geometries or some. But yeah, I think some part of the story will go through for other operas. But
people have definitely tried to capture parts of string theory in that style, right? There's that whole work on modular operads, string theory.
Right. Yeah. No, I don't have anything more clever to say about it.
And also, if we try to do like non-quadratic quadrats where we'll have like valence higher than 2.
Yes, sure, of course. Well, already for L infinity, you can have more inputs. You can also consider, people also thought about putting props there rather than operas, but then of course, well, to some extent, you can also work with that, and that would correspond to some kind of field theory with the action which is of higher order in B, in the B field. But that immediately creates way more diagrams, but still you can play with it. The question is like, where do you want to go then? If you want to go to triangulations, then there are extra problems then if you try to do that.
More questions? Okay, then let's thank Pavel. Right now we have a coffee break and we'll resume at 11.